Hi everyone, welcome back to third lesson on electric field. I hope that everyone had gone through the previous recorded lessons. If any of you haven't done it yet, please complete those two lessons before starting the third one. As usual, I would like to give you a recap of lesson 1 and 2 before starting the third lesson. So here I have highlighted the important concepts we have learned in the previous classes. We have learned about Coulomb's law. As we know, Coulomb's law will help us to find the magnitude of the force acting between two point charges. The equation for Coulomb's law is F is equal to K times Q1 Q2 over R square. After discussing Coulomb's law, we have done uh, electric field and how to calculate the strength of the electric field using the equation E is equal to F over Q. The representation of electric field using electric field lines also covered in the previous classes. We know that there are two types of electric field, which are uniform electric field and radial electric field. Out of these two, we had a detailed discussion on uniform electric field in the previous class. In addition to these topics, we had discussed thermionic emission also. Let us see what are the objectives of today's lesson. By the end of this lesson, you will be able to explain what is the meaning of a radial electric field, how to represent a radial electric field using field lines, and we have to derive an expression for calculating the intensity of radial electric field also. After discussing the main objectives, we will be discussing few important types of questions that we can expect from this part of electric field. In the previous lesson, we have learned about electric field. We know that it is a region around a charged particle where another charged particle experiences a force of attraction or repulsion. Also, we know that there are two types of electric fields, which are uniform electric field and radial electric field. What's the meaning of uniform electric field? Yeah, in a uniform electric field, the field remains the same everywhere in it. So let us see what's the meaning of a radial electric field. Another name of radial electric field is non-uniform electric field. So from this term, it is very clear that the magnitude and direction of electric field is going to be different in such an electric field. Yes, the magnitude or direction or both changes from point to point in a radial electric field. So this is completely different from a uniform electric field, right? In uniform electric field, both magnitude and direction of the field remains the same everywhere. But in radial electric field, it would be different if you take different positions in such a electric field. See, here you can see a positive source charge. I have taken 2 points A and B. They are having different distance from this positive charge. Hence, the magnitude of electric field will be different at positions A and B. At the same time, the direction of field will be radially outward. So here in this example, though the directions of electric field is same at position A and position B, their strength is different. Similarly, if you take another position C, uh, since position or point A and C are equidistant from the positive test charge or positive source charge, the magnitude of the field remains the same at A and C, but the directions would be opposite. We know since this is a positive test charge, in our explanation it will be radially outward, it will be going this way, other one will be going this way. So as I mentioned in the previous statement, the magnitude is different at A and B, but direction is same. Magnitude is same at A and C, but directions are different. If you take position B and C, the magnitude of electric field is different, directions are also different. Here you can see two examples for radial electric field. Both fields are produced by point charges. The first one is the radial electric field produced by a positive charge. It could be a proton. And second one is the radial electric field produced by a negatively charged particle also, maybe an electron. Here the field lines are radially inwards, and in the first example field lines are radially outwards also. Dear students, look at this radial electric field produced by a proton. As you can see, the arrows get further apart as you move further away from the proton. We know that the density of the field lines represent the strength of the electric field, which means the density of the field lines are higher near to the charged particle, and the density is decreasing as you move further away from it. This indicates that the field strength reduces as you move away from a point charge. So the strength of the radial electric field is different at different points. What is the meaning of electric field strength? We have defined it in the previous class. Electric field strength at a point in an electric field is the force per unit positive charge placed at that point. That is, E is equal to F over Q. Next, we are going to derive an expression for electric field strength due to a point charge. Here we have a source charge Q, and there is a point P which is a distance r away from the source charge, where we have placed a test charge small q. Now we are planning to derive an expression for electric field strength due to the source charge capital Q at the point P. From the definition, electric field strength E is equal to force over the charge which is placed at that point. That is, if you cross multiply, we can write Q times E is equal to F, or QE is equal to K times QQ over R square. To calculate the electrostatic force on simple Q due to capital Q, we are using Coulomb's law. According to Coulomb's law, F is equal to K times Q1 Q2 over R square. Here Q1 is capital Q, which is the source charge, and Q2 is the test charge with magnitude simple q. We can cancel q from both sides, and we got an expression for electric field strength, which is E is equal to KQ over R square. So this is the expression for electric field strength due to a point charge. If you want to calculate electric field strength at a point, which is the distance r away from the source charge, we have to use this equation. So electric field strength E is equal to KQ over R square. When K and Q are constants, the electric field strength is inversely proportional to the square of the distance from the charge. That is, E proportional to 1 over r square. So electric field strength due to a point charge is also obeying inverse square law. What does it mean? If you double the distance, electric field strength decreases by a factor of 4. So using the inverse square concepts, the product of E and R square will be always a constant. So electric field strength due to a point charge depends on magnitude of the charge and distance from the charge. Next, we are going to discuss about electric field strength against distance graphs. As we know, electric field strength is obeying inverse square law. So look at the first graph. Here we have taken electric field strength on y-axis and 1 over r square on x-axis. Since E and 1 over r square are directly proportional, we can say this is a y proportional to x graph, which means we get a straight line which is passing through the origin. Electric field strength is obeying inverse square law. So the second graph is an example for y proportional to 1 over h square graph. So we get a graph like what I have shown here. We have discussed about the standard shapes of the graphs in the previous lessons. And in third one, here we are taking E on y-axis and r square on x-axis. This is an example for y proportional to 1 over x graph. So we get a curve like what I have shown on this graph. Remember, the variation of field strength with distance is commonly tested in your exams. So you need to able to recognize and reproduce the above graphs. If you have any confusion regarding the standard shapes of the graphs, you can refer to the previous recorded lessons. Next, we are going to discuss about electric field produced by a hollow charge sphere. Remember, the net electric field strength inside a hollow charge sphere is always 0. So inside this hollow sphere, though it is a charged one, the electric field strength remains 0. At the same time, outside this sphere, the field behaves as if all the charge creating it is at a point in the center of the sphere, which means you can assume that the entire charge on this sphere is located at a single point at the center. So the electric field pattern would be exactly similar to the electric field produced by radial electric field produced by a point charge. Now, if you plot electric field strength against distance for a hollow sphere, this would be the shape of the graph. Look, up to R0, what is R0? It is the radius of the sphere. Up to R0, the electric field strength is 0 because we know inside the sphere electric field strength is always 0. Then outside the sphere, the electric field obeys inverse square law. We know this is the shape of that inverse square relationship. Let us compare radial and uniform electric field. Here I have listed the important properties and examples for both. In radial electric field, magnitude or direction of both of the electric field varies from point to point. At the same time, in uniform electric field, magnitude and direction of the electric field remain the same. And example for radial electric fields are electric field due to point charges like field produced by an electron, proton, etc. At the same time, the electric field between two parallel charged plates which are charged equal and opposite, right, according to this diagram. It will be an example for a uniform electric field, and here you can see an example for radial field pattern also. Dear students, rest of the discussion of today's lesson is based on the questions asked in the previous papers. Here I have 4 different models which are purely based on radial electric field. This is a type 1. In this question, you are requested to calculate electric field strength at a distance of 5 centimeters from the surface of a positively charged sphere. See, here is the sphere. We have a point somewhere here which is 5 centimeters from the surface of the sphere. And since this is an example for a radial electric field, to calculate the field strength, we have to use the equation E is equal to kq over r square. So K is Coulomb's constant and Q is charge of the sphere. I have substituted both values, and while doing the calculation, don't forget to convert nanocoulombs to coulombs. So the conversion is 10 to the power minus 9. Then we have to substitute the value for R. What is R? It is the distance from the center of the sphere to the point where we are calculating the strength of the electric field. So in order to calculate R, we can use this information. They gave diameter of the sphere which is 12 centimeters. So its radius is 6 centimeters. By adding that 6 and 5, you will be getting 11 centimeters, which is the distance from the center of the sphere to the point. So we have substituted that value. The conversion part is also done, and we get this answer in Newton per Coulomb. So magnitude of electric field strength is 25.3 kilonewton per Coulomb. And this is a positively charged sphere. It's a radial field too. So the direction of electric field is radially outward from the center of the sphere, which means an arrow passing through this point this way. In this second type of question, they are asking us to calculate distance in meters from an electron at which electric field strength equal to 6.4 times 10 to the power 8 Newton per coulombs. So here you are requested to calculate the distance due to a point charge. This is also an example for radial electric field. So we use the equation E is equal to kq over r square. Substituting the data given to us, we get 6.4 times 10 to the power 8, which is E, equal to Coulomb's constant times charge of the electron divided by square of the distance. Making r square subject, you will be getting the expression like what I have written here, and value for r would be 1.45 times 10 to the power minus 9. So the answer which is very close to this one is option D. So the right option for this question is option D. In this type, we have to identify the correct graph for a negative point charge, electric field produced by a negative point charge against the distance. So as you know, the strength of the electric field is varying. So option A and C are wrong. So the correct option would be either B or D. Since here we are talking about negative point charge, electric field would be negative. Hence, the correct answer is option D. In this question, we have to calculate the resultant electric field strength at the point X due to this polar molecule. To calculate electric field strength at X, we have to calculate field produced by both point charges separately at X and then we have to use vector addition to find the resultant electric field. Here you can see the direction of electric field at X due to the positive charge, which is radially outwards, and direction of electric field due to the negative point charge, which is radially inward. Since they are acting in different directions, we have to split both vectors into their components, I mean rectangular components, and then we have to solve to get the resultant electric field. Here you can see the angles made by both electric field vectors, and these are the components of electric field produced by the positive charge. The horizontal component is E cos 43 and the other component is E sin 43. Similarly, we have splitted electric field due to the negative charge also into two rectangular components with horizontal component E cos 43 and vertical component E sin 43. Distance from both charges to the point X is same. Hence, the magnitude of electric field strength at X due to both charges are also the same. If you look at the vertical components, their magnitudes are equal but acting in the opposite direction. Hence, they cancel each other. So, the resultant electric field would be the sum of the horizontal components produced by both charges. That is, resultant electric field is equal to 2 times E cos 43. Now we have to calculate electric field due to one of the charges separately. We don't need to find both differently because their magnitudes are equal. Using the equation for radial electric field, E is equal to kq over r square. Substituting the values will give you 3.18 times 10 to the power 10 Newton per Coulomb. So this is the electric field produced by both charges at the point X. Now, to get the resultant electric field, we have to substitute the value for E in this equation 2 times E into cos 45, which will give us 4.65 times 10 to the power 10 Newton per Coulomb, which is the magnitude of resultant electric field at the point X. This question is based on uniform electric field. Here you are requested to find the direction of electric field at point P due to all the charges on the plates. In this question, I can show you the key points. Remember, electric field shows the direction of force on a positive charge. So if you want to know the direction of electric field at P, assume that we have placed plus 1 Coulomb charge at this point. If you consider the charge just above, this positive charge just above this test charge, this positive charge will be pushing it downward. Similarly, this negative charge also will be exerting a force, which will be a pull, which is also in downward direction. If you take this particular positive charge, the direction of force acting on this test charge would be in this direction. This force could be splitted into two components, right? A horizontal component and a vertical component. That could be cancelled by the force produced by the corresponding positive charge on the right side. So due to this charge, the direction of force or push will be happening in this way. That one also could be splitted into two components, a horizontal and vertical components, and the components parallel to the plate, these are the components parallel to the plate, right? They cancel out. At the same time, you know, the vertical ones will be added up. So the field at P is perpendicular to the plate from positive to negative. So here I have taken just two charges only. Similarly, you can do with other charges also. So the components parallel to the plate to the left all are balanced by components parallel to the sheet to the right. So these are the equations we have learned so far. Coulomb's law using inverse square concept, Fr square is a constant. Electric field strength is force per unit positive charge. By cross multiplication we get F is equal to QE. Using Newton's second law, Ma is equal to QE or A is equal to QE over M. Equation for uniform electric field, E is equal to V over D, where V is the potential difference and D is the distance between them. By cross multiplying, V is equal to E times D. And these are the two equations we have added in lesson 3. Equation for electric field strength due to a radial field. If you want to know the strength of a radial electric field, which is a distance r away from the source charge q, E is equal to kq over r square. And this is also obeying inverse square concept. Hence, E r square is also a constant. And you can find the constants also. Coulomb's constant, charge of an electron, mass of the electron, mass of the proton, and conversion of electron volts to joules. As usual, we have two follow-up activities from lesson 3 also, assignment 1 and assignment 2. Please submit both assignments on time. We need one more lesson to complete electric field. So to be continued in electric field lesson 4. Thank you for watching.